through the answers on this. Sydney is me. Ready, set, go.
Okay. Roddy.
Atoms are composed of 3 particles, protons, neutrons, and electrons.
What?
The top.
He's doing the top.
I
We can run through the top as quickly as possible, then she'll fill in the table for us.
I'll do the numbers.
Okay.
12 neutrons, 11 protons.
Aaron.
6 electrons and 6 protons.
Let's do fluorine. Malak.
10 neutrons, 9 electrons. No, it said 9.
Oh, okay.
Good answer.
Ella.
16 electrons and 32 for the atomic mass.
Allie.
92 protons and the atomic mass of 238.
38. Chad.
47 electrons and the atomic mass of 108.
Okay.
All right. Questions about how we arrived at those answers? Anybody need any clarification questions? 107?
Yeah.
Oh, yep. It turns out the ones that are on your test you don't actually need a periodic table for, but Lucas, you weren't here Friday, correct?
Yes.
Do you need someone to tell you how you determine the number of protons? Excellent. Who would like to tell Lucas how we determine the number of protons in any element?
Because that eraser's not working.
Well, if you have the neutron number, you can subtract the neutron number from the atomic mass, and then you have the proton number and the electron number, since atoms on the periodic table are electrically neutral.
What if I just gave you a periodic table? What number would you look for?
The atomic number.
Excellent. Look for the atomic number. Does the number of protons in an element ever change? Number of protons in an element always remains the same, right?
Oh, God.
What is the mass?
Okay, it's back.
You know,
No,
what is the
it's broken.
mass of
Eraser's not working.
Isn't that how you guys do it when you don't have whiteout? You're just like, just scribble it out. So atomic mass minus atomic number. And what's the mass of one neutron in AMU? Mikey?
1 AMU.
And electrons. What can you tell me about electrons?
Virtually massless.
And since these atoms are,
Neutral.
then what is the number of electrons?
The same number as protons. Same.
Okay, so that's Friday in a nutshell, right? And we said everybody on the periodic table gets personality or their identity from the number of protons. So everyone on the periodic table at atoms. They do something very similar. There can be types of any atoms of any element. So atoms of any element can come in different types. That type is actually not much different than my example. They're called isotopes. And all they are atoms of different mass but the same identity. So the number of protons remains the same, because remember we said that's like the social security number. That's the identity. Number of protons remains the same. What changes is the mass of the element. Now for the mass of the element to change, we're not going to change the number of electrons, because remember you said they're virtually massless. And if the number of protons remains the same, it must, because the identity stays the same, what's the one thing that changes about that atom?
Neutron.
It's the number of neutrons that changes. Now, changing the number of neutrons occasionally does change the behavior of that element. And what I mean by the behavior, well, sometimes it just changes the mass and it's no big deal. Our friend hydrogen exists in 3 different isotopes, and we'll go through those 3 isotopes. That change in mass doesn't make a huge difference. But then other elements, when you change that number of neutrons, it makes one behavior particularly different. It makes them radioactive. Carbon, our friend carbon does that. So we're going to look at 3 different for these 2 atoms and see if we can't see the difference between the 2. Hydrogen has 3 isotopes. Hydrogen 1, hydrogen 2, and hydrogen 3. You'll notice when we abbreviate an isotope, we simply write the symbol and then the mass number. So that refers to the mass. So this is mass number. We'll start with the number of protons. Hydrogen is element number 1 on the periodic table. How many protons does it have? 1. Fabulous. And that's going to be the true for every isotope, right? Because that never changes. How about electrons? Is that ever going to change? Still an atom, so we've got 1 electron. Hydrogen 1 has a mass of 1, and it has 1 proton. How many neutrons does it have?
0.
Hydrogen 2 has a mass of 2, has 1 proton. How many neutrons does it have?
1.
Hydrogen 3 has 1 proton. How many neutrons does it have?
2.
Those are your isotopes. These are all completely naturally occurring isotopes. They just exist in variations throughout nature. That's why when you look at the periodic table, you'll notice that it says 1.001 and some numbers for hydrogen. It's not an even mass because any sample, like if I were to take a beaker and fill it with hydrogen, which would be like totally a challenge since it's a gas, but whatever. If I were to take a beaker and fill it with hydrogen, it's going to be a combination of these 3 different isotopes. It's not going to be all 1 isotope. They call it natural abundance. It turns out the most common one is hydrogen 1. See if you can't do the same thing for your carbon isotopes. You've done it before, haven't you? That first isotope of carbon, how do I know how many protons carbon has? What did I have to consult?
Either your prior knowledge or the periodic table.
Prior knowledge or periodic table, and if you consulted those things, you would find it in the 6th box on the periodic table. Being in the 6th box tells you it has how many protons? And because you are enterprising young honors biology students, you know that anytime I give you an atom, it's neutral. So you're going to tell me how many electrons does it have every time?
6.
So, how many neutrons?
C12 has 6, C13 has 7, and C14 has 8.
Which one of these is radioactive? That one is the radioactive one. We learn these isotopes because it turns out that these are the ones that are biologically the most important for us. This is how we date how old certain samples are. We can measure how long it takes radioactive elements to decay into their products because radioactive means unstable. And that means it's going to, since it's unstable, it's going to work its way towards stability by decaying into another element. So they will decay. We can look at a sample then of carbon, and based on the amount of carbon-14 to the amount of its product, what it decays into, we can estimate how old something is. Turns out, though, carbon is only one isotope we use to do that. Do you think we use carbon-14 to date really old things or really young things? Old from whose perspective?
Humans.
As it turns out, we actually use carbon-14 to date relatively young things. Things that are younger than 20,000 years old. That's young. We use the radioactive isotopes of potassium to date really old things. That's a couple billion years.